Right, so fuels. There are a few fossil fuels. The one you need to know in detail is crude oil, and you need to know that it is a mixture of hydrocarbons. That word mixture is important. They give you multiple choice questions where they change that word, so make sure you know it's a mixture of hydrocarbons. Because it's a mixture, it can be separated. You'll separate the mixture using fractional distillation. The reason we can use fractional distillation is each fraction or each part of crude oil has a different BP, which means different boiling point. If we have a look at what fractional distillation looks like, okay, so here is my fractionating column. I put my crude oil into the fractionating column and I heat the crude oil, okay, so there's my fire. You heat the crude oil. It is currently a liquid. You heat a liquid and it will evaporate and it will turn into a gas. So you get evaporation. That hot vapor is going to rise up the column, and when it rises up, it will cool down, and then that gas will turn back into a liquid. So you get condensing further up the column, okay? The column is hottest at the bottom, that's where you're heating it. It's coldest at the top. So once that liquid is turned into a gas and the vapors rise, they will cool down. And when they cool down, they'll condense again and they'll be collected at different points in the column. Remember, we can use this technique because all my different fractions have different boiling points. So these are my fractions that I get. So remember, fractions just means parts, the different parts of crude oil, and you need to know them in order. So gases, petrol, kerosene, diesel oil, fuel oil, and bitumen. You need to know the 6 of them and in that order. You also need to know a use for each one. The reason we go through this process of fractional distillation is the mixture of crude oil, when these guys are all mixed together, is not useful, but when you separate them all out, each fraction has a different uses. So petrol we obviously use as a fuel for cars, bitumen we use to tar roads and roofs. You need to know those uses. The other thing you need to know are these certain trends that I've got listed here at the side. So if we start at the first one, as I go down the column, each fraction becomes more viscous. Viscous just means thick. So I would say ketchup is a viscous liquid. It's thick and it's difficult to pour. So bitumen at the bottom is the most viscous. It's the hardest to pour. It's like tar. And then gases at the top. Gases are very easy to pour because they flow over each other. As you go down the column, BP increases. That means boiling point increases. Bitumen is the highest boiling point. Gases have the lowest. As you go down, the size of the molecules increases. So they're all still made up of hydrocarbons. The hydrocarbons in bitumen are the biggest. The hydrocarbons in the gases fraction are the smallest. And as you go down, they become harder to ignite. A lot of these are used as fuels. For a fuel to release energy, you have to set it on fire. That's why I care about how easy it is to ignite. And bitumen down at the bottom is difficult to ignite. We don't use it as a fuel. We use it to tar roads and roofs. It's difficult to set on fire. Gas is very easy to ignite. You've got gases in your Bunsen burner taps. We know how flammable they are. They're easy to ignite and therefore they're good as fuels. Okay, so this is your fractionating column. You need to know these details as well as these trends. The other thing they'll ask you is to explain these trends. Why do they get more viscous? Why does the boiling point increase? Okay, and for both of those you've got exactly the same answer. You'll say the molecules get bigger. Okay, so the molecules get bigger, and this means that you have got more / stronger intermolecular forces. These guys, hydrocarbons, are all molecules. There's intermolecular forces between them, and as the molecules get bigger and bigger, you've got more, or you can say stronger intermolecular forces between the molecules, and that means you need more energy to overcome them. So that same answer there will explain why they get more viscous down the group. It also explains why the boiling point increases down the group. All right, bigger molecules, stronger intermolecular forces, more energy required to overcome them. The last little thing we're going to look at is hydrocarbons themselves in a tiny bit of detail. So hydrocarbons, you can call them molecules or compounds, and they've got carbon and hydrogen only. You need to say that word only to get the mark. There are so many different hydrocarbons that we put them into families, and we call these families homologous series. And there are two different ones that you need to know. You need to know the alkane homologous series and the alkene homologous series. Now, to be a member of a family, you need to meet 4 criteria. The first criteria is you need to have the same general formula as all other family members. The general formula for an alkane is CnH2n plus 2. So every member of the alkane family has that general formula. And if you're in the alkene family, you've got it CnH2n, no 2. Okay, so if I practice using that, if I let n equal 1, that means I would have 1 carbon. I've got 2 times n, 2 times 1 is 2, 2 plus 2 is 4, I've got 4 hydrogens. If I try that with a slightly larger one, let's let n equal 2. If n equals 2, I've got C2. For H, I've got 2 times 2 is 4, 4 and 2 is 6. So what my general formula tells me is that I've always got double the number of hydrogens plus 2. Alright, if I did it with 3, I'd have double the number of hydrogens, which would be 6, plus 2 is 8. Over here for the alkene, the smallest alkene member has got 2 carbons in it, and I've got exactly double the number of hydrogens, C2H4. If there was 3, C3H6. So the alkane family, double plus 2, the alkene, just I'm doubling. The other thing I can say about members of the families is successive members differ by a CH2, and we can see that here. By successive member, I mean the next member in the family. So I'm going from C1 to C2 to C3. And as I go from one member to the next member, you can see all I'm doing is adding a CH2. I'm going from C1 to C2 to C3, so I'm adding a carbon each time. I'm going from H4 to H6 to H8, so I'm adding 2 hydrogens. It's the same over here. As I go from one family member to the next, I'm adding 1 carbon, I'm adding 2 hydrogens. And you can say that about all members of a homologous series. The other thing you can say about members of a homologous series is they have similar chemical properties. Chemical properties refer to chemical reactions. And all of the alkanes react in a similar way. All of the alkenes react in a similar way. Annoyingly, you can't say same chemical properties, you have to say similar. The last thing that members of a family have in common is they show a trend in physical properties. A trend in physical properties. Physical properties are things like melting point and boiling point. And by trend, you've got an exam question on it here, all right? Boiling point would be a physical property, and the trend I see is that as the number of carbon atoms in the alkane increases, the boiling point gets higher. So I can't say that all alkanes have a low boiling point, because some of them actually have quite a high boiling point, but I can see a trend. As the number of carbons in the alkane molecule increases, so does my boiling point. So just be really mindful that it's similar chemical, but a trend in physical properties. That's what it takes to be a member of a homologous series, these 4 things. It's a common exam question. The last thing I'm going to do very quickly is just draw you a few alkanes and alkenes so you can see what they look like. So if I were to draw C2H6, which is an alkane, it's double plus 2. You draw the 2 carbons side by side, and then you put the hydrogens around the outside. Carbon has to have 4 bonds, so I join the 2 carbons and the 6 hydrogens go around the outside. If I were to do this with 3, I join the 3 carbons in a row and I would put all of the hydrogens around the outside, making sure I have got 4 bonds on every carbon. So that was C2H6. This here is C3H8. If I'm drawing out alkenes, my simplest alkene is C2H4. Okay, I put the 2 carbons next to each other. Okay, and because it's an alkene, I know it's going to have a double bond. There has to be a double bond between the 2 carbon atoms. So I'm going to put that in straight away. Then I'm going to fill in my hydrogens. I've got 4 hydrogens in total. 1, 2, 3, 4. 4. Every carbon now has 1, 2, 3, 4 bonds. If I do it for 3 carbons, 1, 2, 3, draw your 3 carbons. You know there has to be a double bond. It doesn't matter where you put the double bond. I'm going to put it here at the end, and then you fill in the hydrogens. A common mistake here, okay, is to put 2 hydrogens on each carbon. But remember, you have to end up with 4 bonds. This carbon currently only had 1, so I need to put 3 hydrogens on it to bring it up to 4. This carbon has 3 bonds, it only needs 1 hydrogen. This carbon has 2 bonds, so it needs 2 hydrogens, and that's what that one would look like. You do also need to be able to name them, but it's nice and easy. If there are 2 carbons, it always starts with ETH. If it's 3 carbons, it starts with PROP. If you had 4 carbons, it's BUT, and if you only had 1, it's METH. The ending then depends on the homologous series. If it's an alkane, it's ane, and an alkene is ene. So this is an alkane, so it will be ethane. This one is the alkene version, ethene. This is the alkane, propane. The alkene version, propene. This one, if I drew it out, would be 4 carbons, butane, and this one I would draw out 4 carbons, 1, 2, 3, 4. You put the double bond someplace, wherever you want to, and then you fill in hydrogens to make sure that every carbon has 4 bonds. I need 3 at the end, 1 there, and 3 at the end, and this would be butene.